So now on the INM, we are given a quadratic function and a linear function, which is defined by the table below, and we are asked to find the solution or solutions to the quadratic linear system. So recall that the solutions to a quadratic linear system are the points where f of x equals g of x, or in this case, where f of x is equal to h of x. In order to answer this INM question, I know that I need an equation for f of x, which I already have, but I need an equation defined for h of x. So if you go back to your Algebra 1 skills, you can see that each output, h of x, is 6 greater than the input. 7 is 6 greater than 1, 8 is 6 greater than 2, 9 is 6 greater than 3. So I'm going to define h of x is x plus 6. So now, I know that I'm looking for the point where f of x is equal to h of x. So I'm going to set those equations equal to each other. F of x equals h of x. And I'm going to substitute in my two equations. X squared plus 5x plus 6 is equal to x plus 6. And just like I did in the think about it, I can use these two equations and combine them so I have one single quadratic. So I'll subtract x from both sides. X squared plus 4x plus 6 equals 0. Sorry. X squared plus 4x plus 6 equals 6. And then I can subtract 6 from both sides to end up with x squared plus 4x equals 0. So now I need to determine how many solutions there are and what the solutions are to this quadratic. So the easiest way to solve this quadratic is actually by factoring. You could solve it using the quadratic formula, but it'll take you a little bit longer. So I'm going to show you how to solve it by factoring. I know that both of these have an x term, so I can factor out an x, and I end up with x factored out times x plus 4 equals 0. This is going to make it really easy for me to determine the zeros of the quadratic because I just have to set each factor individually equal to 0 to find the solutions. So remember that 0 times anything is equal to 0, so x could be equal to 0. Or I can set this other factor equal to 0 and say that x is equal to negative 4. So it appears that there are two places that the graphs of f of x and h of x will intersect. In other words, there are two solutions to this system, but I've only found the x values of the system, so I now need to find the y values that satisfy the system as well, so I have ordered pairs that are solutions to the system. So it's much easier to substitute into h of x. So I have that equation, h of x equals x plus 6, and I'm just going to substitute in to find h of 0. And I see that h of 0 is 6, and h of negative 4 is negative 4 plus 6, or h of negative 4 is equal to 2. This then tells me that my solutions are 0, 6, and negative 4, 2. These are the points that satisfy both h of x and f of x. And we can double check that these satisfy f of x by substituting them in to the original equation for f of x. We'll just do one of them to check. So 6 equals 0 squared plus 5 times 0 plus 6. We end up with 6 equals 6. That one checks out. And let's just do it for the other one as well. So f of x equals x squared plus 5x plus 6. We substitute in 2 equals negative 4 squared plus 5 times negative 4 plus 6. We end up with 2 equals 16 minus 20 plus 6. 2 equals 2. And this checks out as well. So for the second part of this problem, I'm asked to write an equation for h of x such that the system has only one solution. So in other words, I want there to only be one point of intersection. In the first part of our INM, we saw that we actually had 2 points of intersection. We had 2 solutions. Now I'm looking for only one solution. So the easiest thing for me to do, for starters, to help me get a sense of what's happening, is to graph this on my calculator and to draw a sketch of it. So when you graph it on your calculator, you should have something that looks like this. It might be a little bit hard to see, but I just entered the equations for h of x and f of x into my calculator. And then I can also make a sketch of this scenario. So what I know about the scenario is that my 2 graphs intersect at 0, 6, so I'm going to make sure to plot that point, and at -4, 2, so I'm going to make sure to plot that point as well. I can connect these 2 points. This gives me my linear equation. This is h of x. And I know that my quadratic, x squared plus 5x plus 6, by looking at this graph, I can see that it is concave up. You also know that from the leading coefficient. I can also see that it just barely dips below the x-axis, and it has to go through these 2 points here because we already established that those were solutions to the system. So in order to make sure that my sketch is most accurate, I'm actually going to use my calculators. I can use my calculator to find the zeros so that I make sure that I'm graphing in the right place. So you know how to find zeros on your calculator. I see that one of the zeros of this quadratic is at -2, 0. So I'll graph that here. I can find my other value. My other 0 is going to be at -3, 0. So right here, it's going to dip. My vertex is going to be at the bottom. You could have also just found the vertex. There's a variety of ways to do this. But when I graph this, I hope your graph looks prettier than mine. That is the rough parabola that defines f of x. So if I'm only going to have one solution, I need to move one of these graphs down or up such that they only touch one time. The easiest way for me to do this is just to move my linear equation to a point of intersection that I already know, where the line will be tangent to the parabola. So think back to geometry. Remember that a tangent line touches something at one place. So I'm looking for a way to make this line tangent to this curve. The easiest thing for me to do is to translate h of x down until it touches this 0, which is at -2, 0. So I am going to figure out what is the x value right here. I'm sorry, what is the y value that has the same x value as -2, so that I can slide down my graph along this line, x equals -2, so that the line just touches the parabola at one place. So I can evaluate h of -2. So I remember that h of x is x plus 6. H of -2 is -2 plus 6. H of -2 is 4. So this point is at 2, 4. I know I need to get it down to 2, 0 if the line is only going to touch the graph at one place. So I need to translate h of x down 4 units, because that's how far it is to get from 4 to 0. When I do this translation downward, you'll be able to see, if you do it on your calculator, that the new line for h of x will only touch the graph at one place. So when I translate h of x down 4 units, I know that's a translation of the outputs, so I am looking to take h of x minus 4, which is h of x minus 4 is equal to x plus 6 minus 4, or x plus 2. This makes sense based on the sketch that I just drew. My line in my sketch looks like it goes through about the point 0.02 as the y-intercept. So the new equation for h of x is x plus 2. That is the transformation that will give our system one solution.